Earth's magnetic environment changed rapidly, fast enough that space weather monitoring centers around the world were closely tracking what was happening. As the morning progressed, NOAA's Space Weather Prediction Center updated its main dashboard from a geomagnetic storm watch to a severe geomagnetic storm alert, as measurements crossed key thresholds. Now, based on observations pulled this morning at around 10:30 a.m. or so Eastern Standard Time, today being January 20th, 2026, Earth had already reached G4 status, a severe geomagnetic storm level. So what does that mean in practical terms? And why does it matter beyond space science? So when a geomagnetic storm reaches this level, multiple parts of Earth's space environment change at the same time. Energy from the sun interacts with Earth's magnetic field, and that interaction affects systems that depend on precise timing, stable signals, and predictable conditions. So today, in this video, I'm going to walk through how the measurements lined up earlier today, step by step, and how those measurements connect to everyday technologies people rely on without even thinking about it. I'm Dr. Amanda Fetch, aka Dr. Amanda Analytics, and I focus on how space weather data is interpreted and used for real-world decision-making. So let's first start with what was measured, because each signal adds context to the next. So this geomagnetic storm was driven by a coronal mass ejection, or a CME, which is a large release of solar material and magnetic energy from the sun earlier this week. And as that material traveled through space and reached Earth, instruments monitoring near-Earth conditions recorded coordinated changes that triggered NOAA's storm classification. Now, those changes are what we can measure and what operators use to assess risk. So I'm going to now talk a little bit about how NOAA determines storm severity and what each measurement connects to in everyday life. So GO satellites measure solar X-ray activity, reaching C-class levels. And so this data shows us there was a peak around a C4.2 earlier today. Now that measurement reflects how much energy was released at the sun and helps indicate whether solar eruptions are capable of driving disturbances that reach us down here on Earth. Now, in practical terms, this is part of how forecasters assess whether solar activity has the potential to affect Earth-based systems. Now, as that CME arrived, the planetary K-index reached values between an 8 and a 9, which corresponds to a G4, which would then be a severe geomagnetic storm. Now, the K-index runs again from a 0 to a 9. Now, values this high indicate strong global disturbances in Earth's magnetic field. Now, at this level, systems that depend on stable magnetic and radio conditions, for example, like GPS navigation, aviation systems, and some communication networks, now they could start to experience some increased uncertainty. Now, solar wind speeds increased to approximately 800 to 870 kilometers per second. Now, that is more than twice the speed of typical background solar wind. Now, at the same time, the interplanetary magnetic field's BZ component dropped to around -7 to a -8 nanotesla and remained southward for several hours. Now, this orientation allows energy from the solar wind to enter Earth's magnetic environment more efficiently. Now, that strengthens geomagnetic storms and increases stress on space-based and ground-based systems. Now, during geomagnetic storms at this level, organizations responsible for critical systems monitoring, well, I should say for critical systems, they monitor these conditions closely. And so that can include things like satellites adjusting for increased atmospheric drag, GPS systems managing positioning accuracy, aviation monitoring radiation exposure at flight altitudes, radio operators tracking signal reliability, infrastructure operators watching for timing and communication anomalies. Now, these systems are designed to be resilient, but geomagnetic storms increase the likelihood that operators need to intervene or adjust operations. Now, the challenge with space weather is deciding how to respond as conditions evolve. Now, measurements can change over hours. Impacts can vary by system, and decisions often involve trade-offs between caution, cost, and continuity of service. Analytical approaches, including AI-based clustering and anomaly detection, can help identify patterns across multiple signals, which earlier supports more informed decision-making about when to act. Now, as solar cycle 25 continues, events like today's geomagnetic storm are expected to occur more frequently. Now, for those not familiar, solar cycle 25 is the current phase of the sun's roughly 11-year or so activity cycle, during which solar storms, flares, and geomagnetic disturbances become more frequent as the sun approaches its peak activity. Now, that makes understanding how these measurements connect to real-world systems increasingly important for us. Now, today's geomagnetic storm shows how activity on the sun translates into measurable conditions that affect technology back here on Earth. Now, I have a question for you to think about. As space weather events become more frequent, how should decisions be made about when to adjust operations that us down here on Earth rely on every day? I'd love to hear your thoughts in the comments. Thanks for watching this video. And if the content resonates, would love to you subscribe. Thanks for tuning in. Take care.